This lecture starts the beginning of the last unit of the semester, and we start with buffers, which I like to say is equilibrium on steroids. And so it's complex and in-depth, so it takes quite a few brain cells. So buffers are really cool, actually, and we use them a lot in our lives. One of the most important buffer systems is the one in our body, okay? It is a buffer system that controls the pH of our blood, which needs to be quite close to neutral if we want to stay alive. There are several other applications of buffers maintaining the pH of a swimming pool, basically any system at all that needs to have a relatively stable pH. So the definition in general is any solution that resists change in pH. And how it does that is the buffer itself contains a bit of an acid and a bit of a base. Though weak, you'll see the types that are required. And because of that, though, if a bit of acid or base as a contaminant ends up being added to a system, the inherent weak acid and base that the buffer has itself will neutralize these contaminants. So what a buffer contains then is a mixture of a weak acid and its conjugate base. Okay, so we're used to showing that generically, right, as this. So this would be our weak acid and this would be the conjugate base. So these two, both present in a buffer, or a weak base and its conjugate acid. So we have shown that all right, there we go. So how do buffers work? Well, they have a certain amount of a weak acid and its conjugate base, or a weak base and its conjugate acid. Let's look at one just to make it seem more real. Acetic acid and its conjugate base acetate. If those are both added, and you'll see in roughly equal amounts to a buffer system, they will control the pH. And what happens is, let's kind of look at it figuratively. We have both of these molecules present in the buffer. So if a base contaminant is accidentally introduced to the solution, the weak acid will react with that basic contaminant. Now, here's the key. Look at what's formed when a base contaminant, we're just assuming it's a hydroxide, reacts with the weak acid to control the buffer. If you were to write out that reaction, the product, in addition to just water, right? The product of that is the conjugate base of the acid that just reacted. So you are simply making more of the other component of the buffer. So if that doesn't make sense right away, look at it for a moment or a couple moments and see if you can get it to make sense, because that's important in understanding how a buffer works. Through that, if we were to add an acidic contaminant too, okay? So again, here's your buffer system. We're just assuming for argument's sake that it's acetic acid and its conjugate base acetate. Let's say now that we introduce an acidic contaminant, something with an acidic hydrogen. Which of these two buffer components will an acidic component react with? Well, of course, the base. But what does it make when an acid reacts with this base? So here it's larger over here, right? All of the base reacts with the contaminant acid to regenerate the other half of the buffer, which is acetic acid. So the bottom line is these two components of a buffer go back and forth if the buffer system is contaminated. So you end up with just slightly differing amounts of the weak acid and its conjugate base, depending on what contaminants have been introduced to the solution. What else do we have to consider when we're making a buffer? What conditions make the most effective buffer? Well, first of all, we want the concentration of the weak acid and its conjugate base to be roughly equal. An effective buffer can vary a bit from a ratio of 1 to 1, but it's recommended that the ratio stays within a factor of 10. Okay, so you might have 10 times more of the weak acid than the conjugate base, or vice versa, but not more than that. And a buffer, we call it buffer capacity. How much contaminant can it handle? Obviously, the buffer capacity is going to be higher when you add more of the weak acid and its conjugate base, okay? The more you have, the more contaminant they're able to consume. Then we talk about buffer range. Okay, so what range of pH is a buffer system able to control? Well, the rule of thumb is that you want to pick a weak acid whose pKa is plus or minus 1 from the pH that you want to maintain the solution at. So let's say I want to maintain a solution at a neutral pH of 7. That would mean that in order to do that effectively, I would need to pick a weak acid whose pKa was 7 plus or minus 1. So anywhere from 6 to 8 would, pKa of 6 to 8 would create a buffer system that would be able to control the pH at around 7. So here's an example, and you can expect a multiple choice type question like this on your next unit exam. So this question is saying, okay, we want to create a solution that'll be buffered at a pH of 9.2, which, and we're not going to do this yet. We can do that toward the end of the PowerPoint. Which of these following weak acids should we pick in order to get a pH of 9? Well, this was deliberately thrown off, okay, because if you're talking about a pH greater than 7, that means that you want a base. You want a basic system, right? But the rule of thumb and what we're used to working with is pKa, not pKb. So this table, you would think you would look at this one because you want a basic buffer, right? But remember, we want pKa plus or minus 1 from pH. So we've got to convert these KBs to, or PKBs to pKa's. So let's just add another column. Remember, to get from pKa to pKb, it's just 14 minus. So if you go through and write all the pKa's for these. All right, so now let's look at the pKa values and find the closest we have to 9.20. And that would clearly be ammonia. All right, so how the heck do we figure out the pH of a buffer system? If you think about it, it seems pretty complicated because you have a weak acid, right? And we know how to calculate the pH of a weak acid using an ice table, but in that buffer system, we also have a weak base. And we could set up an ice table for a weak base. What happens if you have both of them? Well, as you might imagine, it depends on the ratio of the weak acid compared to its conjugate base that you have present, right? And although you won't need to derive this equation we're going to ultimately use for the pH of buffers, I do want you to know where it comes from. So if you were to look at the generic equilibrium of a weak acid, you would set the expression up like this, but you could rearrange that to solve for hydronium ion concentration. And by doing so, you can kind of see it's easy to get the ratio of the original weak acid to its conjugate base in a mathematical form that's easy to use. Now, if we take log of both sides of this rearranged equation, we get what is called the Henderson-Hasselbalch equation, and that's the equation we're going to use to find the pH of a buffer system. What's kind of nice about the Henderson-Hasselbalch equation is that because we are dealing with the ratio of conjugate base to conjugate acid, they don't have to be in concentrations. This is a really important point that'll save you time on an exam or quiz, okay? Because units are going to cancel, right? So if we have units of concentration for each of them, right, we're going to get the same value as we did if we simply had moles of each of them. Okay, now you can't use grams, right, because the different quantities, your apples to oranges. But anyway, you can use the Henderson-Hasselbalch with either concentration or moles. Now look for a minute what happens when you have equal amounts of the weak acid and its conjugate base. That ratio goes to 1, right? And what is log of 1? Log of 1 is 0. So if the concentrations of the two components of the buffer are equal, then pH of the system simply equals the pKa of the weak acid you've used to make the buffer, which is pretty cool. That's also a really important point, okay? That'll show up on my exam as well as the final exam. So here's a sample problem. So now you just have to be able to identify the weak acid and its conjugate base. I think it's pretty clear here is the weak acid. What may not be so apparent to you is that the sources of weak bases are typically salts. Okay, the sources where we get weak bases from are salts or ionic compounds. What am I talking about? So if you have a salt, an ionic compound that's soluble in water, we know that it's going to immediately dissociate into the ions. And what is this? This is the conjugate base of the weak acid we're using, right? Sodium is not going to do a thing. It doesn't change the pH of solution. Now, you do want a cation. We've learned about how some cations and anions can affect the pH. So you definitely want to pick a salt that has ions in it that are not capable, well, the spectator type ions that we're not using as a conjugate. You don't want them to be able to react with anything or change the pH of solution. All right, so we've identified now what the conjugate base and its weak acid are. And so let's go ahead and plug into the Henderson-Hasselbalch equation. Alrighty, here it is. So here's the Ka that was given to us. There is the ratio of, now in this form of Henderson-Hasselbalch, and there are different forms, so be careful again. You'll see Henderson-Hasselbalch in terms of POH. Just be careful. They're all correct, but whichever one you choose, don't merge them together, okay? So in this form, we have the conjugate base on top, which is 0.2. The weak acid is in the denominator, and that is 0.5. And we then calculate that the pH of this buffer solution is 8.91. Pretty easy, huh? So that is just how you find the original pH of a buffer. We are going to be continuing how to learn how to find the pH if we contaminate that buffer. So if we throw in a little bit of an acid or base, it's going to change the pH of the buffer, but how much? As always, there are different versions of a buffer question that you can be asked. It's not always going to ask you to solve for the pH. Sometimes it'll ask you to solve for the ratio of the original weak acid and its conjugate base. You can solve for anything. So here's an example of just a different wording. This one wants you to calculate the moles of sodium acetate. Now remember, that's the salt that gives us our conjugate base, acetate, right? That must be added to a solution of acetic acid, which is our weak acid, in order to prepare a pH 4.68 buffer. How I approach this problem, just in case it's useful to you, is as soon as I know it's a buffer problem, and I think that's pretty obvious, anytime you have the presence of a weak acid and its conjugate base, or a weak base and its conjugate acid, you've got a buffer. I immediately write down the Henderson-hasselbalch and plug in everything that I know, everything that's been given to me, okay? So I can plug in, they told me the pH that I want. They gave me the Ka, so I can calculate pKa, right? So pKa is minus log of Ka, and pKa then is 4.74. Okay, and they are asking me to solve for acetate, so that's going to be what I rearranged to solve for. And they have told me the concentration of the weak acid. So I can do one of two things. I can either plug in the concentration of the weak acid that they gave me, 0.16, but then what I'm going to get when I rearrange this equation is the concentration of the conjugate base, and then I'll have to convert that to moles, because notice they're asking for moles of the conjugate base, not molarity. But I know, if you remember me telling you at the beginning of this PowerPoint, that the Henderson-hasselbalch equation works if I use moles for each, the weak acid and the conjugate base. And if I used moles of the weak acid right now, when I solve for A minus the conjugate base, it'll come out in moles, and that'll just save me a step. So I'm going to go ahead and do that. I can get moles of the acetic acid. So just to kind of remind you, molarity equals moles per liter. And if I rearrange that to solve for moles, it would be molarity times liters. So that's what I'm doing right here. So the moles of acetic acid, liters is volume, right? They gave that to us. I just converted it from milliliters to liters. And here's the molarity. So, right, liters are going to cancel, and there are the moles of the weak acid. So let me go ahead and plug everything in to Henderson-hasselbalch, pH, pKa. I'm solving for the moles of acetate, and here are the moles of acetic acid. All right, so how do you simplify that? It's a logarithmic equation, so we've got to use, it's log base 10, so we've got to use the 10 factor to get rid of the log. First thing you're going to do, though, is subtract 4.74 from both sides so that you have your log term on its own. Now, to get rid of log base 10, we're going to raise, both sides will become an exponent for 10, right, which makes the log go away. And then just rearrange, multiply both sides by 0.040 so that you can solve for moles of the acetate ion. And your final answer, 0.35 moles of the conjugate base is needed. All right, so here's another depth. So you may want to practice just simple buffer pH calculations before you move to this step. So the whole reason buffers are made are to control pH if contaminants are added. So we need to be able to calculate the change in a pH when a contaminant is added. So I always kind of like to give overviews of how you do a calculation. Here's an overview of how to do a buffer contamination problem. The first thing that you are going to do is a stoichiometry problem using the balanced reaction to determine what the contaminant has done to the moles of the original weak acid and its conjugate base than you had in buffer. So you remember, if you add an acidic contaminant, it's going to chew up or react with some of the conjugate base. So you're going to end up with less of the conjugate base and more of the original weak acid. Okay, so we have to go through moles to calculate the change. And then step 2, after you figure out the new mole values of the weak acid and the conjugate base, then we're going to use the Henderson-Hasselbalch equation. So I think the best way to teach this is to go through it stepwise, and feel free to stop the video at any point and back up. It can be complicated to understand. So I'm going to do 2 problems here. One, I'm going to add hydrochloric acid as a contaminant to, first of all, pure water, just so you can see it's going to make a massive change in the pH of something that's not buffered. And it's not that much HCl, okay? It's only 0.1 molar. It's pretty low concentration, but it's still going to mess up water pH like crazy. And then I'm going to add the same amount of HCl to a buffer. And you're going to see that this is a very small change in pH. This probably represents the trickiest type of calculation you're going to have on this unit. All right, so let's do the water first, okay? We know the initial pH of pure water. When we get to the buffer problem, we're going to have to calculate. In order to calculate change in pH, you have to know the initial pH, right? So the buffer contamination, we're going to have to first calculate the pH of the buffer uncontaminated, and then do a whole separate problem to find the pH after it's been contaminated. All right, so we know that HCl is a strong acid. So we know that the concentration of H+, or that's equivalent, right, to H3O+, is going to simply equal the concentration of the original acid. So what we've essentially done here, I'll go over this formula in a minute, but I want to kind of explain it first. So we know that to get moles, you can multiply volume times molarity, right? So if I multiply, I have 10 milliliters, if I switch that to liters and I multiply it by the given molarity, I can find out how many moles of HCl I contaminated the solution with. All right, so here are the moles. Now, that's not the ultimate concentration of HCl, though, because I dumped it in another solution. If you go back to the problem, it started with 100 milliliter solution. So we added this 10 milliliters of HCl to 100 milliliters of water. So to find the new concentration of HCl, it's going to be 0.0010 moles that we just calculated, divided by the total volume of the solution, which is the 100 milliliters of water, 0.100 liters of water, plus the 10 milliliters of HCl. So the molarity of HCl that contaminated or was added to pure water is 0.0091 molar. Now, having gone through that to maybe help you understand what happened, there's something called the dilution formula, which, and hopefully you've used that before, but anytime you combine 2 solutions, and in this case, we added a small amount of an HCl solution to water, so we added 2 liquid things together, you're diluting everything in both of them, right? And so this dilution formula will work. So all it's saying is really the moles that you had in the first set, which is HCl by itself, equal moles that you have after it's diluted. Okay, so we didn't change the moles of HCl, we just diluted it. That's where it comes from. Molarity times volume is moles. Anyway, remember this solution formula. Anytime you mix two or more things together, that will help you easily figure out the new concentration. All right, so bottom line, since HCl is a strong acid, we know that its concentration that was added to the water is going to produce exactly the same amount of hydronium ion. It all dissociates. And so we simply take the minus log of that new concentration, and here is the pH. That's it. Okay, that's how you calculate the pH for strong acid, right? It's just the minus log of whatever the original concentration was. So the pH change in pure water, it started out pH 7 when it was neutral, and then we dumped in that 10 milliliters of 0.1 molar HCl. That's not very much. And it changed the pH down to 2. So remember, pH is a log scale. So a pH change of 5 means factor of 50, right? It's an exponent. So we have changed the hydronium ion concentration by a factor of 50. Alrighty, the more complicated calculation to do is to calculate the pH change that occurs in a buffer system when the same contaminant is added. So before calculating the change in pH, we have to know the original pH of the buffer. So Henderson-hasselbalch, of course, we're going to use that for both of them. The problem told us that it was acetic acid and its conjugate base acetate. And so that's how we know the pKa. And then plugging in the values they gave us for the buffer. This is just information that was given. It was 100 milliliters of a solution containing 1.5 molar of the weak acid and 1.2 molar of its conjugate base. Now, we didn't have to change these into moles, right? Henderson-hasselbalch can use concentrations, so we could have simply plugged in the concentration of the acetate, which was 1.20, divided by the concentration of the acetic acid, which is 1.50, and you get exactly the same answer. I just want you to be able to do both cases. All right, so the pH of the original buffer is 4.65. Now remember that the pH of any buffer system, you want it to be as close to pKa as possible. Now you see why. The Henderson-hasselbalch equation shows how close they are to each other. All right. I mentioned when you contaminate a buffer that you need something called a mole table. I call it mole table because it's very similar to an ice table, but it uses moles instead of concentration. That's really important, okay? We're doing stoichiometry, and so we want moles. We don't want concentration. All right, so from the last page, we calculate moles of the original acetic acid and the conjugate base. Now, if you want to, what is millimoles? Okay, millimoles is, let me go back to molarity. Remember, if you want to calculate moles, it's molarity times liters. In titrations and buffers, chemists often just work with milliliters instead of liters. So if you keep your volume in milliliters, it just saves you a step. Instead of converting it to liters, what you'll get is millimoles. It just saves you a step. You can still convert to liters if you want. All right, so here are the original millimoles. Now, when you're working with buffers, we're used to in an ice table, the products are typically start out at 0, right? They're not going to in a buffer. You're going to have some conjugate base and acid both there. All right, so how do you know the change? the change is going to represent the contaminant. Okay, so, and again, everything has to be in moles. So remember, we had 10 milliliters of a 0.1 molar solution of HCl, right? So that tells us we have, if we keep it milliliters, we have 1 millimole of HCl or H3O. Now, you have to ask yourself, which of the buffer components is the acid going to react with? It's always going to react with the base, right? Acids react with bases. So you have to write the correct equation for your mole table. In other words, you would never write, you wouldn't put the weak acid reacting with another acid, right? So just get the right thing reacting. All right, so now we're going to assume that all of the contaminant, in this case acid, is going to react. And it's going to react with the base. So that's why it's minus 1 millimole. The acid should always be gone at the end of your mole table. It all reacts. And what do these two make when they react with each other? They make the original weak acid, acetic acid. Okay? Remember, an acid-base reaction is simply moving a hydrogen ion from one substance to the other. That's all we've done. So make sure you can write out products of an acid-base reaction. All right, so now we have the new amounts of the weak acid and its conjugate base. So we can plug these new quantities. Remember, you can keep them in moles or millimoles, and solve for pH. So here's the pH after acid contamination. What was the pH to begin with? It was 4.65. Unreal. So we only changed the pH with this acid contaminant by 0.01. And remember, we changed it 5 whole units in pure water. So that kind of gives you an idea of how effective buffers can be. And that's it for the first lecture in this last unit. Please begin practicing right now on buffers, okay? There's an easier worksheet and then there's a more challenging one. Work as many as you possibly can.